Hi guys. Okay, today we're going to talk about concavity and the second derivative. So let's remember, the graph of a function is concave up when its derivative is increasing. That's when the rate of change is increasing. Now, if something is increasing, its derivative should be positive, right? Well, what do we call the derivative of the derivative? That's the second derivative. So if the second derivative is positive, our function is concave up. Similarly, our function is concave down when its derivative is decreasing. That means that the rate of change is decreasing. And if something is decreasing, its derivative, the second derivative, is negative. And our function is concave down. So if you look, as these slopes get less and less steep, they're concave down. And as these slopes get steeper and steeper and steeper and steeper, we were concave up. Okay, now there's one more word here. The point where the concavity changes, which in this picture is right here at the origin, is called a point of inflection or an inflection point. Okay, so it's important to realize, and I've got the same picture here so that you can see it again. When the derivative is decreasing, the slopes are decreasing, the second derivative is negative, the graph is concave down. Over here, when the derivative increases, the slopes are getting steeper, the second derivative is positive, and the graph is concave up. Okay, now as x increases, the slopes are decreasing. In this particular problem, the second derivative is less than 0. We say on the open interval from negative infinity, or for all the x is less than 0. F of x is concave down. Notice we use an open interval. When we did increasing and decreasing, we had closed interval. Concavities are open intervals. Also notice when a graph is concave down, the curve is below the tangent line, right? As x increases, the slopes are increasing, or the second derivative is positive. In this case, we're on the open interval from 0 to positive infinity, or the x is greater than 0. F of x is concave up. Again, open interval, and this time when we're concave up, the tangents are below the curve. Okay, real important to know. So to sum this up, if the second derivative is less than 0, then the graph of f of x is concave down. And if the second derivative is greater than 0, the graph of f of x is concave up. And possible, because it's more than just this part, possible points of inflection are those values of x where the second derivative is 0 or where the second derivative does not exist. Now remember, I said it's only possible points because a point of inflection is where the concavity changes, and concavity only changes if the second derivative changes sign. So you only have a point of inflection if the second derivative equals 0 or doesn't exist, and the second derivative changes sign. Okay? So when you're analyzing a graph of the first derivative, now here's the thing. We can look at a graph of a first derivative and determine whether the function is concave up or down. Because if you're looking at the graph of the first derivative, if the graph of the first derivative is increasing, remember that only happens when its derivative, f double prime, is positive, right? Which means the graph of the function is concave up. When you're looking at a graph of the derivative, if you have the situation where the first derivative is decreasing, remember, that only happens if the second derivative is negative, then that's where the function is concave down. So if you're given a graph of f prime, your reason for concavity should have nothing to do with the second derivative. It should have to do with whether the derivative is increasing or decreasing. Let's take a look at this. This is an example from 2015, AB5. The figure below shows the graph of f prime, the derivative of a twice differentiable function f on the closed interval from -3 to 4. The graph of f prime has horizontal tangents at -1, at 1, and at 3. So they're showing us where the maxes and mins are, okay? On what open intervals contained in -3 to 4 is the graph of f both concave down and decreasing? Well, let's break this up. If f is concave down, right, that's when the second derivative is negative, but that means that f prime is decreasing. So we want to know where this derivative is decreasing. Well, it's decreasing all through here, and it's decreasing all through here. And we want f to be decreasing, and that only happens when the derivative is less than or equal to 0. So that's in here and in here, right? Now, since we don't include these points for the concavity, we're not going to be including them here either, okay? So these critical points are not going to be included because they don't get included for concavity. So we're really looking, okay, where our graph is below the x-axis and decreasing. Well, we already highlighted it. Now we just need to write it out. So the graph of f is both concave down and decreasing on -2 less than x less than -1 and 1 less than x less than 3, since f prime of x is decreasing and negative. There's your answer and your reasoning. Okay, suppose we have a function given to us in symbolic form. If you're given an algebraic representation of a function, you're going to find the second derivative. You're going to set it equal to 0 and find those critical values. And you're going to do a number line. You're going to do that sign analysis. You're going to do the number lines with positives and negatives, just like we do with the first derivative. Then you can answer the question. Remember, intervals where the second derivative is positive or where the function graph is concave up. When the second derivative is negative, the function is concave down. So here's an example. H of x is x cubed minus 6x squared minus 7. What are all values of x where the graph of y equals h of x is concave down, and justify your answer. So first we have to find h prime of x, which would be 3x squared minus 12x. Then we find the second derivative of h, which would be 6x minus 12. Now that is always going to exist, so we need to know when the second derivative is going to be 0. Which means 6x would have to equal 12, or x would equal 2. Okay, so I'm going to make my number line, and my only number on it is 2. We're going to label the top with the second derivative, the bottom with our function. If I pick a number smaller than 2 and we plug it in here, say 0, 6 times 0 minus 12 is negative. Take a number bigger than 2, like 100, 6 times 100 minus 12 is positive. Now when my second derivative is negative, my function is concave down, and when my second derivative is positive, my function is concave up. We want to know when our function is concave down, so therefore, the graph of h is concave down for all the x's less than 2, since the second derivative of h of x is less than 0. And there we go. Now just a quick word about justifications. Justifications of intervals of concavity require a statement of causal connection between either the concavity of the graph of the function and increasing, decreasing nature of the derivative graph. So if you're given a derivative graph, then you can tell us it's increasing or decreasing, and that's what affects the concavity. If you're given analytic, we can also look at the concavity of the graph if the sign of its second derivative is positive or negative. Also, justifications of points of inflection require several things. The first derivative changes from increasing to decreasing, or decreasing to increasing. The second derivative changes sign, or the first derivative has an extremum, a maximum or minimum. If the first derivative has a max or a min, it changed from increasing to decreasing, which means the derivative changed sign. So again, if you're looking at a graph of a derivative and you see that it has a max or a min, then you know the original function has a point of inflection. Now, here's an example. Where does the graph of y equals the quantity x minus 2 raised to the 1/3 have a point of inflection? Give a reason for your answer. Okay, so points of inflection, we need to look at the second derivative. So first, we need the first derivative. So we bring down the exponent 1/3, keep the inside, subtract 1, we get 2/3 times the derivative of the inside is 1. Now we're going to take the second derivative. So 1/3 times negative 2/3 is negative 2/9. Keep the inside. Our new exponent is negative 5/3. I'm going to rewrite this as negative 2 over 9 times x minus 2 to the 5/3. Now, if you look at this function, the numerator is negative 2. That's never going to be 0. However, this second derivative will not exist when the denominator is 0, which happens when x is 2. So when we make our number line, 2 is the number on the number line, d squared y over dx squared, and then y. So if we take a number smaller than 2, say 0, and we plug it into this second derivative, we're going to have what kind of a number? Well, this part will be negative, and that part, so we're going to have negative and negative, which is positive. We pick a number bigger than 2, say 100, we got a positive, we'll cube positive, and 9th is positive. Negative over positive is negative. That means that our function is going to be concave up and then concave down. So now we're ready to say that the graph of y has a point of inflection at x equals 2 since the second derivative of y with respect to x twice does not exist when x equals 2, and the second derivative of y with respect to x twice changes from positive to negative at x equals 2. And all of that is needed for your answer. All right, some common misconceptions. Number 1, the second derivative does not need to be 0 in order to change sign. Okay, you can have a vertical tangent line. That means that there's a 0 in the denominator that has no slope. Therefore, it fails to exist. This is that problem. This is the graph of that problem we just did. The second derivative doesn't exist there. Therefore, we have a possible point of inflection. Second misconception is just because the second derivative is 0 does not mean it must change sign. And this is something that kids get caught on all the time. I don't know why. You guys don't do it with maxes and mins, but so often kids will just tell me, well, the second derivative is 0, so therefore I have a point of inflection. No. Right here, we have an example where the second derivative is 0 at 0, but that second derivative never changes sign. It is not a point of inflection of the original function. Okay, be really careful that the second derivative must change signs. So the second derivative test is also for a max min. Now, if we know that the derivative is 0, okay? That means we have a possible max or a min. And normally, we would test the derivative to see if it's changing from positive to negative or negative to positive. However, sometimes we don't have enough information to do that. So, if we know we have a critical point there because the derivative is 0, and we know that the second derivative is less than 0, that means the second derivative is negative, so the function is concave down, okay? The function is concave down. Now, if you think about that, if it's concave down and we have a horizontal tangent line, what kind of point do we have? We have a relative max. So if you know that the derivative is 0 and the second derivative is negative, you are guaranteed to have a local maximum at that x value. Now let's take a look at a local min. So again, if the derivative is 0, so we know we have a possible max or min, we have a horizontal tangent line, okay? And then we know that the second derivative is positive. That means the function is concave up. So let's sketch ourselves a graph that's concave up, right? If it's concave up, and we know there's a horizontal tangent line there at C, what do we have on our graph? We have a relative minimum or a local minimum. Okay, so this is pretty awesome, and it can be quite helpful. We can use this whenever we know f has a critical point, okay, and the derivative is 0. The tangent line to f of x must have a slope of 0, not where the slope doesn't exist, okay? So we need it to be that the derivative is 0, not that f prime doesn't exist. And if we know whether the second derivative is positive or negative. This test is really useful with the optimization problems that we're going to be doing in a day or two. Optimization problems are like finding the minimum cost, finding the maximum profit, minimizing the amount of materials we need to use. This test can be really useful in those problems. It makes it easier. Now, notice what we didn't talk about, but if the second derivative is 0, the test is inconclusive. It means we can't use this test. We have to go back to the first derivative, or we just don't have enough information. So that's important to realize. If you look at the graph, when we have the derivative is 0, because we have that green horizontal line here, and this highlighted purple portion is concave up, that's because the second derivative is positive. We have a relative min. Same thing over here all the way on the right. We have another horizontal tangent line and a purple concave up part. Second derivative is positive. It's a relative min. And then in the middle here, okay, at B, we have a horizontal tangent line, but now our graph is concave down, and we have a relative maximum, okay? Let's try an analytic problem. Let's try one, okay? So here we have g of x is 2x squared minus the natural log of x for x greater than 0. We're going to identify the x value of the critical point of g of x, and we're going to classify the point as a relative maximum, minimum, or neither, and we're going to use the second derivative test, just so we can try it once, okay? So we have g of x is 2x squared minus the natural log of x. So if we want to take the derivative of 2x squared is 4x minus the derivative of the natural log of x is 1 over x. So we want to know when the derivative is 0. So that would mean that 4x has to equal 1 over x, or 4x squared equals 1, which means x squared is 1/4, or x is positive and negative, square root of 1/4 is 1/2, but we know that x has to be greater than 0, right? Don't forget that piece up there. So x has to be positive 1/2, okay? So we now know that g prime of 1/2 is 0. Now, let's get our second derivative. So our second derivative, we need to take the derivative of the derivative. So the derivative of 4x is 4 minus, now remember, This is x to the negative 1. So the derivative of x to the negative 1, we bring down the negative 1, keep the x, raise it to the negative 2. So this is really 4 plus 1 over x squared. So now what we need to do is we need to find the value of the second derivative at this x value, 1/2. So that means 4 plus 1 over 1/2 squared. Well, that's 4 plus 4, which is 8. Now that is a number that's greater than 0, which means that f is concave up. So think about it, concave up, and we have a horizontal tangent, we have a relative min. So notice, if you just know you have to find when the derivative is 0, okay, find that x value, and plug it into the second derivative. Don't memorize when it's positive, it's a minimum, when it's negative, it's a maximum. Look at the picture. Let's draw a picture. Okay, it's concave up, it's curved like this, I have to have a min. Okay, so now we get to write our answer. Therefore, G has a relative minimum at x equals 1/2, since we never write anything without a reason. G prime of 1/2 equals 0, and G double prime of 1/2 is greater than 0. And there we go, we've done one. Okay, here's another example. Selected values of a twice differentiable function, so that means the first and the second derivative both exist. H of x and its derivatives are given in the table below. Which of the following statements must be true? Now notice also, if it's twice differentiable, we also know it's a what type of function? It's continuous, right? Okay, so notice these. We're talking about an absolute maximum, concave down, relative maximum. All right, let's take a look. Well, I see that the only 0 here in the derivative is here at 7, right? When x is 7. The derivative is 0, and my second derivative is -4, which is less than 0, which means my graph is concave down, which means we have a relative maximum at x equals 7. Oh, look at that. That's one of our choices. Yay! So we actually found the answer already. Now, why don't the others work? An absolute maximum at x equals -4. This is talking about when the second derivative is 0. That's not going to tell us maxes and mins. For B, concave down from 3 to 7. Now, it is true that the second derivative is -3 and the second derivative is negative at 7, but I have no idea what's going on in between 3 and 7, so I cannot make that assumption. All right, and we know it's not D because we already showed that C is true. Awesome. All right, so that's all we wanted to cover for now on the second derivative test, but we'll work more on that in class, and I will see you guys soon. Have a good one.